Hello statistics students, my name is Jami Emigh, and this video will start our discussion on chapter 6, title Normal Probability Distributions. Section 6.1 title, the Standard Normal Distribution. We're going to talk about how area can be used to find probabilities. For example, given the graph of data with uniform distribution, that means rectangular shaped, we're asked to find the probability that a randomly selected voltage level is greater than 124.5. So we're asked to find a probability, but we're given a graph. If we can find the percent underneath the rectangle that's shaded in, that will lead us to the probability. Let me show you. Okay, underneath the rectangle here, we've got a height of 0.5. I got that from right here, okay? And a base of our rectangle, 124.5 to 125.0. That is a distance of 0.5. Now, this shape right here is a rectangle. We know to find the area of a rectangle, we do the base times the height. So we'll do the 0.5 times 0.5. 0.5 times 0.5 is 0.25, and that means that the capital P probability, open parentheses, that one randomly selected, were these batteries? One randomly selected voltage level being greater than or equal to 124.5. We close our parentheses, and that is equivalent to the area that we found, or 0.25 can also be written as 1/4. The same can be done for data with standard normal distribution. So that means the bell-shaped curve with z-scores on the horizontal axis. Here is a picture. This isn't new to us. We've seen this before for the empirical rule, 68, 95, 99.7, standard normal distribution, bell-shaped curve. We're asked to find the probability that a randomly selected variable has a z-score between -1 and +1. So we're going to do the same thing. We're going to find what percent of the bell is shaded in. For this one, it's between, they want us to check between -1 and +1. So we're being asked, what's the probability of randomly selecting a data value and it being in this shaded region? Well, this shaded region makes up 68% of our bell-shaped curve. So we would write that as capital P for probability, open your parentheses, z-score is between -1 and +1, and that's going to be equal to not 68%, but remember as a probability that would be 0.68. Let's do it again for this request. Probability of, we're looking for z-scores greater than or equal to 0 this time. Close your parentheses. All right, let me erase my last shading. So now I can shade this request here. Z is greater than or equal to 0. So these would be z-scores of 0, and then greater than or equal to would be everything shaded on this side of 0. So if we can figure out what percentage this is, well, that will lead us to the probability of randomly selecting a data value and having a z-score greater than or equal to 0. Well, you could just eyeball it. Doesn't this look like half? You'd be right. You could also add up these percentages right here. That'll get you to 1/2 or 0.5, or 50%. But remember, we write that probability as 0.50, not as 50%. Okay. All right, let's keep going. This time we're being requested to find the probability of a z-score greater than or equal to -1. Let me erase this last stuff. Okay, greater than or equal to -1. So our shading this time needs to start at -1, and then we shade in the greater than direction. So it's going to be all of this stuff. So just using what we had from the last one, this is half. We know all of these right here added up to half of the bell, or 50%. So we just need to add this much more to it so that we get the entire thing. So 34.13 plus all of these right here, which we know add to 50. So plus 50, it's going to give us, adding these together, 84.13. 84.13% of the bell is shaded in, and so we would report that back as the probability of 0.84. Okay, one more. Probability that z is less than or equal to 2. I'm going to erase all the old stuff and go again. Okay, read it carefully, what's in the parentheses. Z needs to be less than or equal to 2. So I'm going to make a cut right here at 2, and then I'm going to shade everything less than or equal to that. So this time we're shading in this direction. So to figure that percentage of the bell that's shaded in now, we would have to add up everything. And if we add all of these up, it'll be approximately 97%, and then we would report back as the probability of randomly selecting a data value and it having a z-score less than or equal to 2 as 0.97. All right, so I hope you're starting to pick up on this idea here that area can be used to find probability. Let's look at the program that we're going to use. For standard normal distribution, and that's when the z-scores are on the horizontal axis, we have mu equal to 0, sigma equal to 1, and the area under the entire curve is 100%, but we report that as a probability of 1. Okay, what we see here is an example of a StatCrunch output screen. Notice for this particular example, the word between is selected, and that is going to give us a graph between two z-scores, should that be our task. Mean, or mu, is right here as 0. Standard deviation, or sigma, is right here as 1. And then in this inequality statement, we put our two z-scores. So for this one, it's between -2 and -1. That's why you see these values here. Okay, z-scores go here. And then what follows the equal sign is the probability. You can think of this as a percentage if you want to. So this probability of 0.1359 and so on means approximately 13.59% of the bell is shaded in. Sure, looks like about a little less than 15%. Okay, look at the difference on this one. Standard is selected, not between, okay? And you'll use standard if, for example here, we're looking for a probability not between two z-scores, but rather something like this, less than 1.03. So this z-score right here is 1, sorry, it's hard to see. Mu is equal to 0, sigma is equal to 1. That's because we're in z-scores. And what follows the equal sign is the probability portion. So you can think of this as 0.85 probability means that 85% of the bell is shaded in. Yeah, looks like about 85%. Let's compare that to this one. It looks quite different, but if you look closely, it's still in standard because we're not going between two z-scores. We're starting at that same point. We've just shaded the opposite side. See here? Cutting it right here at 1.03643334. Here in this picture, we've shaded this direction. But over here, same cut, we just shaded the other direction. How can we make that happen? Look down here. Mean is still 0, standard deviation sigma is still 1, but the inequality changed from less than 1.036433 to greater than that. And so the output is now, it's not 0.85 because 85% of the bell isn't shaded in. It's the other 15% on the other side that's shaded in. So I want you to notice that the shading moved to the other side of the z-score when the inequality is flipped. Okay, so these are example output screens from StatCrunch. How are you going to get to them? You're going to open StatCrunch, open the Stat drop-down menu, and we're going to find the menu after that labeled Calculators, and here's the program we're going to use. It's called Normal. Think of that bell-shaped curve, okay? It's shaped like a bell. It's called normal distribution. So find the calculator. Program is called Normal. You'll choose standard or between based on the question. We'll enter mu, and if we're in z-scores, we know that mu is going to be 0 and sigma is going to be 1. But if we're in x values, mu and sigma will likely be different. We're going to select our inequality, just depending on the wording of the question. And then we're going to tell the program whatever's given to us. So we're going to tell the program the z-scores, or if we're not in standard normal z-scores, we'll tell the program the x values. Or if those weren't provided for us, we'll tell the program the probability. That would go after the equal sign. So we got to tell the program what we know. We hit compute, and then we'll get an output screen like one of the 3 we saw on the last slide. Let's try it. A bone mineral density measures are normally distributed. Okay. A bone mineral density test can be helpful in identifying osteoporosis. The results are measured as a z-score. So z-scores mean if it's under that standard normal distribution bell-shaped curve with z-scores on the horizontal axis. Task: find the probability that the result lies between 0.7 and 1.98. Okay, we're going to have a bell-shaped curve. We're asked about between 0.7. It's maybe about, oh, that's negative 0.7, my apologies. 0.7 is about right here. It's between 0 and 1. 1.98 is really, really close to 2. And we're asked the probability between. So the notation for that is capital P, open parentheses, 0.7, less than or equal to. We're going z-scores, but the program has an x. So you can think of x and z as interchangeable. And 1.98, oh shoot, I forgot to squeeze in my less than or equal to, 1.98, close parentheses, and when you hit compute, the output, what follows the equal sign, will be the probability. Okay, we've opened StatCrunch. We go to the Stat menu, Calculators. We're using the calculator program called Normal. Open that program. This is the default, what it looks like. we want to select between. Your goal is to make this graph look like the one we sketched, okay? We are in z-scores for this particular question, so mean is 0, standard deviation is 1. We're being asked to find the probability that the z-score for the osteoporosis bone mineral density test is between 0.7 and 1.98. And when we hit compute, I want you to check two things. Does the graph look the way it's supposed to? And then the answer, which will be right here. Here we go, compute. First thing, does that graph look like it's supposed to? Answer is yes, that's like the graph we sketched. And then the second thing we check is right here. This is the probability in the equals after the equal sign. 0.2, 181, and so on. Let's see what that looks like back in. Okay, we would write that up like this, and the answer follows the equal sign. Nice job. Let's do another one. Find the probability that the result is a reading less than 1.27. Okay, so we're going to put a mark at 1.27. So maybe about here. And the wording is less than 1.27. So the notation is capital P, open parentheses. Z is less than or equal to 1.27. So the mark is right here at 1.27, and the shading would be all the z-scores less than that. So this side. Okay, so now we're going to go to StatCrunch, and we're going to try to make the program look like this graph here. When we hit compute, it will give us the probability or the percent of the bell that's shaded in, or the area. Many ways to think about it. Here we go. Okay, we've reopened StatCrunch. Our old graph is here. You can use it if you want to. You just have to, since the program's already open, just make your changes. So switch it to standard. This particular one is z-scores, so 0 and 1. Ours was bone mineral density test less than, okay, less than, and it was 1.27, okay? Remember, when you hit compute, you need to check two things. 1, does the graph look like the graph you sketched? And 2, the answer, which will be after the equal sign. Compute, does the graph look like the one we sketched? Hopefully yes. If the shading is on the other side, you may have just selected the wrong inequality. Watch what happens. Ready? Watch. Switch in the inequality. Shading moved to the other side. So we want to make sure we have less than 1.27. And then here is our probability that a z-score is less than 1.27. 0.8979578 and so on. Let's see what that would look like. And here we would box the answer, 0.8980. All right, let's try another one. Find the probability that a randomly selected result is above -1. Above -1. So we are going to put a vertical cut right here at -1, and above means z-score is greater than that. So this is what the graph needs to look like. This is what the notation will be. Z is greater than or equal to -1. I want you to go to StatCrunch. Go ahead and pause the video, go to StatCrunch, try to make your graph look like this one. your notation look like this, and your answer will be what follows the equal sign. Go ahead and try that now. If what follows your equal sign was 0.8413, great job, you did it right. And try again. Find the z-score that separates the lowest 15%. Oh, let me talk to you about this one first before you go to StatCrunch. Hold on. Lowest 15%. So the lowest 15% is not a z-score. They didn't give us a z-score this time. They told us the percent shaded in. And they said it's the lowest 15% is shaded in. So what we want to do is start shading in the lowest z-scores. And we kind of just have to guess like when it's going to be 15% of the bell shaded in. Maybe here. Not exactly sure, but at some point our shading will have to stop because we'll have the lowest 15% shaded in. So our question becomes, at what z-score do we stop shading because we have the lowest 15% shaded in? All right, so for this one, you guys, when we go to StatCrunch, we're gonna provide StatCrunch with this information. This information right here will go after the equal sign. Don't type it in as a percentage though, we have to type it in as its corresponding probability. So we'll have to provide StatCrunch with this information. Then when we hit compute, it will provide us with the z-score right here. Let's try it. Okay, we've reopened StatCrunch. Now please take my advice on this, you guys. Clear out all of the old stuff. All of it, okay? Well, the 0 and 1 are going to stay because we're still in standard normal, but make sure you clear out both of these cells, and trust me on this. Clear both of these cells out and do the, let's see, input the provided portion after the equal sign, but I also want to make sure my inequality is right. Let me see which order I want to do that in. After the equal sign, I'll put the lowest 15% it was, and I want to make sure my inequality is less than, because lowest. Okay, this is how you want to have it set up. Make sure you delete both of those first. Now when we hit compute, you're going to check the same two things. 1, does the graph look like the one you sketched? And 2, the answer. But this time, you guys, the answer is not going to be after the equal sign. It's before the equal sign in this cell right here, the one that's empty right now. So when you hit compute, check 1. The graph looks like the one we sketched. And then check 2, the answer, which is negative 1.0364334. Okay, the notation was capital P, open parentheses, z is less than or equal to, and we left this part right here blank in StatCrunch this time. We told the program 0.15, and then it filled this blank in for us with negative 1.04, approximately, if we're giving 2 decimals of accuracy. Okay, so this time we left this part blank, and when we hit compute, that approximately negative 1.04 popped up here. All right, let's try another one like that. Find the z-score that separates the highest 15%. Highest 15%. Okay, highest 15%. So we got to start shading in the highest z-scores. So we're going to be shading in all this stuff. These are the highest z-scores. And at some point, we're going to stop when it's 15%. And we can only eyeball it here, but using our technology, we can get an accurate number, an accurate z-score that separates the highest 15%. Okay, we're going to set it up the same way we did last time. We're going to have capital P, open parentheses, Z. Make sure you switch it to greater than or equal to, and you're going to leave this part blank. You're going to tell the program, well, we know that it's 15%, so 0.15, and when we hit compute, it'll provide us with the z-score right here. Let's see what that looks like. Okay, back to StatCrunch. Take my advice on this, guys. Delete this. Make sure both of those are empty. Let's get our greater than. Provide one of these two. We were given 15%, so that's the corresponding probability, 0.15. So when we hit compute, we'll check two things. One, does our graph look right? Two, the z-score will be in this cell right here. So go ahead, hit compute. Does the graph look right? Yes. Answer is right here, 1.364334, or approximately 1.04. Putting that back in our notes would look like this, 1.04. For us, remember though, it showed up in that blank here. It was like 36, but accurate to 2 decimals, 1.04. Okay. 6.2 is the same program, the same concept. It's just we're talking about real applications of the normal distribution. What that means, you guys, is we're not talking about the z-scores. We would be talking about actual measurements. So we're going to have an X on the horizontal axis this time, and we most likely will not have mean of 0, standard deviations of 1, 2, and 3. We're going to have to get from the data whatever the mean is. We'll type that in here. Whatever the standard deviation is, we'll type that in here. We'll have our inequality, make sure it matches the wording. The X value, which is the horizontal part of the graph, will be here, and the probability will still be after the equal sign. Let's try this one. Tall Clubs International has a requirement that women must be at least 70 inches tall to join. Women have normally distributed heights with a mean of 63.8 inches and a standard deviation of 2.6 inches. Find the percentage of women who satisfy that height requirement. Give your answer accurate to the nearest hundredth of a percent. Okay, that's a very, very long question, lots of words. So I got to kind of back up and I want to see what I'm being hired to do. Find the percent of women who satisfy the height requirement. Okay, I know that the heights are normally distributed. So I'm going to just sketch a bell-shaped curve. I'm going to put an X on the axis this time, not Z. I'm going to put the actual mean in the middle this time, which is 63.8, not 0. That was for z-scores. We have a standard deviation given to us of 2.6. So we've got sigma equals 2.6. And look at this part here. The requirement to join the club is that a woman must be at least 70 inches tall. 70 inches tall, that's up here, that's the tall. And here's 63.8 inches in the middle, that's the mean. So 70 inches we gotta make our vertical cut somewhere up here. We know it's at 70, and we're being asked what the percentage is. So we're being asked what this shaded area is right here. Okay, the notation for that will look like this. The probability, open parentheses, X is greater than or equal to 70, close parentheses, equal sign. And when we hit compute, the answer will be provided for us here. it'll be a probability, and we'll just round it to the nearest hundredth of a percent. Okay, we're back to Stat Crunch. Take my advice, guys. Get rid of this stuff. Okay, now we do have to actually get rid of everything for the first time. Okay, we need to enter the mean height, which was, oh no, I think it was 63.4. I gotta look, I don't remember. 63.8. Okay, 63.8. And the standard deviation was, I forget again, 2.6. I'm sorry. So that goes here, 2.6. And we have a requirement that they have to be taller than 70 inches. So the inequality is the correct one. And we need to say 70 inches here. Okay. When we hit compute, we'll check two things. Does the graph look like the graph we sketched? And then the answer, which this time it will be following the equal sign. Graph looks like the one we sketched, which means this is our answer. That's as a probability though, so we're gonna multiply it by 100. So it'll be 0.854849%. And then we'll round that to the nearest hundredth of a percent was requested. So we'll take that output and round it to 0.85% of women. So that's less than 1% of women meet that height requirement to join this club called Tall Clubs International. Let's do another one. When designing aircraft cabins, what ceiling height will allow 95% of men to stand without bumping their heads? Men's heights are normally distributed with a mean of 69.5 inches, standard deviation of 2.4 inches, rounded to decimal places. Okay, lots of information again. I gotta just slow down, back up. What am I being hired to do? I'm being hired to figure out what height we should make the ceilings in an aircraft cabin so that 95% of men can stand up without bumping their heads. Okay, we know, or we're told, that men's heights are normally distributed. So I'm just sketching a bell-shaped curve. I'm putting X on the axis, not Z, because we weren't given Z scores. We were given the real numbers. Mean height for men from this data set, our population, 69.5. Standard deviation, 2.4. And this time we want 95% of men to be able to stand. So the tallest guys are going to be the issue. They're going to have to duck down. So we're going to start shading in the shortest until we have what looks like 95% shaded in. I think 95% shaded in is going to stop maybe here. All I can do is eyeball it at this point, but then I'll use my technology, or our technology, to figure out this height right here. We want this probability to be 0.95, okay? 0.95. So the notation for that is going to look like this. We're going to set it up as probability that X is less than or equal to. We're going to leave this part blank. We're going to input what we do know, which is 95% or 0.95. And this number right here will be the height or the value on the x-axis that we're looking for. Okay, let's try it. Okay, we're back in Stat Crunch. Take my advice, get rid of all this stuff. Okay, mean height was 69.5. Standard deviation was 2.4. I know that I'm going to need it. We shaded the shorter people, the shorter heights, the shorter x values. So we need x to be less than or equal to. We're leaving this one blank because that's what we're being asked to find. We're putting 0.95 right here because that was the information given to us. When you hit compute, check two things. 1, does the graph look right? 2, the answer, which this time will be here. Ready? Go. 1, graph looks good. 2, the answer, right here. At 73.447649, we would have, on the x-axis, we would have had 95% shaded in. Let's put that back in our notes. That will look like this. And then we were requested to answer with 2 decimal places of accuracy. So we would say we need to make those ceiling heights 73.45 inches inside those aircraft cabins. That'll allow 95% of men to stand without bumping their heads. Okay, last slide for this video. We've got 2 examples. So I want you to pause the video and try them now. Welcome back. Let's see how you did. For the first one, if you got 15.96, you did it correctly. Good job. For the second one, if you got 0.2782, you did it correctly. If you did not do them right, let me help you out. Let's see. Assume that x has a normal distribution. This right here, that word right there, you guys, signals to me to sketch a bell-shaped curve. It says x, so I put that on the axis. Population mean, this right here is mu. That always goes in the middle. Mean, mu, middle, 15.2. Standard deviation, 0.9. Find the x value that separates the top 20%. That's over here. So top 20%, where do we stop shading? Well, just wherever we think it looks like about 20% is shaded in. We can only eyeball it, but technology will get us this accurate x value here. Okay, when you went to StatCrunch, check, did your graph look like this? Did you have your notation set up with x is greater than or equal to, because look, we shade the greater than side. Did you leave this one blank? Did you provide it with the 20% or 0.2 after the equal sign? If you did all of that, when you hit compute, you'll get 15.96. This one here, weekly salaries of teachers in one state are normally distributed. That word right there, you guys, normally distributed. Normal. That's my signal to draw a bell-shaped curve. I'm either going to put z or x. This is giving me actual values, not z-scores, so I put an x. Mean, that's mu. This goes in the middle. Mean, mu, middle. 1650. Standard deviation, 170. This is in dollars. What is the probability that a randomly selected teacher earns less than 1,550 a week? Okay, so 1,150, they provided us with the x value. So maybe it's right about here. So we can only eyeball what percent is shaded in, but if we use technology, it'll get us a more accurate percent shaded in. Okay, so if you set up your notation in StatCrunch, capital P open parentheses, X is less than or equal to, because see we're shaded smaller, less than 1550. If you left this part blank, after the equal sign you should have left blank. Then when you hit compute, you should get a graph that looks like this and a result of approximately 0.2782, which means about 28% of teachers make less than $15.50 a week in this particular state. All right, that will end our discussion for 6.1 and 6.2. Next video, we'll talk about 6.3, sampling distributions and estimators. Thank you for being here. My name is Jami Emigh, and I will see you next time.